Welcome students. So now we'll go for the experimental arrangement for studying Raman effect. So what is this experimental arrangement? First we'll see. So the experimental arrangement to study the Raman effect consists of a Raman tube. This is the Raman tube. So where this is 1 to 2 centimeter in diameter and 10 to 15 centimeter in length. So this Raman tube is having the diameter 1 to 2 centimeter and whose length is 10 to 15 centimeter. One end of this Raman tube, this is drawn into the horn shape. So this is made horn shape, and this horn shape, this is covered with the black color. So why this is covered with the black color? In order to give a perfect background for this photographic camera. If the background is made black, then the phenomena are going to be very clear in the spectrometer. So for that sake, this is covered with the black color. This other end of the glass tube, this is ordinary plain glass tube itself, and this makes a window from which the light, scattered light that comes out, and that phenomenon we are going to see with the help of this spectrometer, where slit will be there, one condensing lens will be there, and again here this is the spectrometer. So this glass tube, this is covered with the water jacket. So here cold water we are going to circulate over this glass tube. So why means in order to prevent overheating of the experimental liquid. So in this glass tube we are taking the experimental liquid, and that liquid should be very pure and it should be free from air bubble. So here over this we are circulating cold water. This cold water that prevents the overheating of this experimental liquid. And next again one more thing. So over this again one more reflector will be there. So this reflector that enhances the intensity of scattered light. So here scattering phenomena takes place, and that scattered light should not escape from this glass. So in order to prevent that, reflector we are going to use, so that intensity of this scattered light that will be more. So for that sake, reflector we are going to use. Next, so here light from the monochromatic source, that is sodium vapor lamp we are using. From that we are going to get the monochromatic light, and that is allowed to pass through the filter. So here filter F we are using. So this filter that allows only this 4358 angstrom meter wavelength light. So here only single wavelength this filter allows, and that falls on this experimental liquid which is very pure, and there the scattering phenomena takes place, and that we are going to see with the help of this spectrometer. If we observe in the spectrometer, so what we are going to see, along with this 4358 angstrom meter, this is the original wavelength that we have sent. Along with this, few lines we are going to, many wavelengths we are going to observe. So this phenomena we can see in the spectrometer, and these lines are captured by using the camera. So if we develop that negative means, so these lines we are going to see along with the original lines. Some more lines will be there, some more wavelengths will be there. So this is original one, and on either side of this original wavelength, again number of lines we are going to see. Few are having wavelength less than the original one, and few are having wavelength more than the original one. So if the wavelength is more than the original wavelength, then such lines are called as Stokes lines. The lines which are having more wavelength than the original line, so that is called as Stokes lines. And here the lines which are having the wavelength less than original one, such lines are called as anti-Stokes lines, and all these are called as Raman lines. So this and this spectrum, so this spectrum is called as Raman spectrum. So here these Stokes lines, they are having more intensity than anti-Stokes lines. The intensity of Stokes lines is more than the anti-Stokes lines, and here it is found that increase their what. The next part in this chapter is, that is quantum theory of Raman effect. So in the year 1929, Professor Smeckel, he tried to explain the Raman effect on the basis of quantum theory. Let us consider a source of light. This is going to emit the photon of energy h nu naught. So consider a source. This is going to emit the photon of energy h nu naught. So when such photon that is going to hit the molecule, so what are the changes that can happen? So that is explained in this quantum theory of Raman effect, and why there are number of lines in the spectrum, so which some are having the same frequency, some are having lesser frequency and more frequency than the original one. So that explanation is given in this quantum theory. So now when photon is going to hit a molecule, then the first change that can happen is, so here consider a molecule, this is the molecule. So when photon is going to interact with the molecule, we have considered the photon of energy h nu naught. So here first case what can happen is, there may be no change in the energy or frequency. If there is no change in the energy, then there is no change in the frequency. So first case is, so when this is going to hit the molecule, photon is going to hit the molecule, there will be the scattering phenomenon, and this is scattered photon that will have the same energy, because there is no absorption either by the molecule or by the photon is neither going to absorb nor going to lose, so that the scattered light that will be having the same energy as that of the incident energy we have considered h nu naught. So here scattered, that also will be having the same energy, that is h nu naught. So here in the spectrum what we have observed, here number of lines we are going to observe. At the middle we are having a line which is having the same frequency as that of the incident one. So here this line is because of this phenomena. There is no exchange of energy between the photon and the molecule. So because of this reason we are going to get a line which is having the same frequency as that of the incident one. So frequency of the incident photon is nu naught, so frequency of the scattered, that is also nu naught. So here we are going to get a line which is having the same frequency as that of the incident one. So this is the first reason. And the second case what it can happen is, when a photon is going to interact with the molecule, let us consider a molecule already there in the excited state. Let us consider E1 is the higher energy state and E2 is the lower energy state. If the molecule is already there in the excited state, so when a photon of energy h nu naught, it is going to interact with the molecule which is there in the excited state, means which is having higher energy, then what happens? The molecule transfers its energy to the photon, means photon is going to absorb energy from the molecule, so that what happens? Molecule loses its energy and it comes to the lower energy state. So here this molecule that comes to lower energy state, and this scattered photon that will be having more energy and more frequency. How much will be there? How much energy this molecule is going to lose is, that is the difference between the energy levels, that is E1 minus E2. So this much difference is there, means that much energy this molecule is going to lose. So here this much is absorbed by the photon. How much this molecule is going to lose, that much the photon is going to absorb, means that much it is going to gain. Already photon is having the energy h nu naught, and how much the molecule is going to lose, that much is absorbed by the photon. So total energy of the scattered photon is this much, that is h nu naught plus this E1 minus E2. If you express this in terms of a frequency, that is frequency of this scattered light, so what we are going to get, that is nu naught, because here this frequency of this scattered energy of this we can express as what? H nu, that is frequency h nu sub s, that is equal to, here this h nu naught plus E1 minus E2 will be there. If you express this only in terms of frequency, then this is equal to nu naught plus E1 minus E2 divided by this h. So this much will be there. Now, so here what happens? The scattered light that will be having more frequency, as that of the incident one, because nu naught plus is there, frequency is increased. So here the line which is having more frequency or lesser wavelength, and that we are going to call as what? Anti-stroke line. So here that I can light as, this is the frequency of anti-stroke line. earlier I had written for the scattered frequency. So now here I can write as for what? Anti-stroke line. Frequency of anti-stroke line is equal to this much. That is nu naught plus, where nu naught is the frequency of incident photon plus this is difference between the energy levels divided by this h is Planck's constant. So this shows that frequency of the scattered light, that is scattered radiation, is increased, and this corresponds to anti-stroke line. So now where the anti-stroke lines are placed here, this before this original one, so this corresponds to anti-stroke line. Next, third case is what? Exactly opposite of this. In the next case, the molecule will be there in the lower energy state. So here energy of the lower energy state we have taken as E2. This is lower energy state. E1 is upper higher energy state. The molecule now here will be there in the lower energy state. So when a photon of energy h nu naught, this is going to interact with the molecule which is there in the lower energy state. What can happen? The photon that can transfer its energy to the molecule. The molecule is going to absorb from the photon so that it will go to the higher energy state, and this photon that is going to lose the energy. So how much energy that is going to lose? That is difference between these two energy states. Already that is E1 is higher energy state and E2 is the lower energy state. Difference between the energy states is E1 minus again E2 will be there. So this much is the difference between the energy state. The molecule goes from what? This lower energy state to the higher energy state. Difference between the energy states is this much, E1 minus E2 will be there. And here the photon originally it is having energy how much? H nu naught is there. So here this photon, this is going to lose energy how much? That is E1 minus E2, this much it is going to lose. So totally the scattered light, again the scattered light that will be having energy of this much. So scattered light that will be having energy of this h nu naught minus of this difference between the energy states, that is E1 minus E2. So here energy of the scattered light, so when the molecule that is there in the lower energy state, this will be there, that is h nu naught minus of this E1 minus E2. Now if I express this in terms of frequency, then I can write as what? Nu s. This is the frequency of again scattered light. This will be equal to, take that h on both the sides and divide, so that we are going to get h nu naught minus of this E1 minus E2, this divided by h. This will be what? Frequency of scattered light, and here frequency is less and the wavelength will be more, and here this corresponds to the Stokes lines. So here this will be frequency of the Stokes line. So why here Stokes line and anti-Stokes line means why the lines are there, so which are having lesser frequency and which are having more frequency than the original one in the case of Raman effect. So that is successfully explained by this quantum theory. So this is the reason why there are number of lines which are having lesser frequency and same frequency and more frequency than the incident one. That is because of this phenomenon. Thank you.